It all began with an unimaginable flash of light, an explosion of such magnitude that it created everything we know. This was the Big Bang. From this singular, brilliant moment, the universe expanded, cooled, and began to form the building blocks of existence. Tiny particles swirled, coalesced, forming vast clouds of gas and dust. Within these cosmic nurseries, gravity, the silent architect, began its patient work. It pulled these materials together, tighter and tighter, igniting the fires of countless stars. Our own sun was one such star, born from a spinning disk of cosmic debris in a quiet corner of the Milky Way galaxy. From the leftovers of our sun's formation, other worlds began to take shape. Tiny grains of dust and ice stuck together, growing into pebbles, then boulders, and eventually into planetesimals. One of these was our own Earth. Imagine a young, chaotic world bombarded by asteroids and comets, a molten sphere of rock and metal glowing in the darkness of space. This was our home some 4.6 billion years ago. It was a violent, inhospitable place, a far cry from the vibrant, life-sustaining planet we know today. The sheer age of our planet is something to marvel at. If you were to represent this timeline on a single calendar year, all of recorded human history would occupy only the last few seconds before midnight on December 31st. This early Earth was not the solid, layered planet we inhabit now. It was a mostly uniform, superheated ball of molten rock, a chaotic mixture of all the elements that had gathered from the primordial cloud. How did our planet transform from a homogeneous molten ball into the neatly layered world it is today? The answer is density. Everything inside Earth was fluid then, like oil and water separating. The heaviest elements were pulled to the center by gravity. Iron, nickel, metals sinking to form a dense core. This is planetary differentiation. Lighter compounds like silicates were pushed upward. The migration wasn't gentle. It was a slow, epic separation that made Earth's structure. How can we possibly know what lies thousands of kilometers beneath our feet? We have drilled only a dozen or so kilometers into the crust, a mere pinprick into the planet's vastness. The answer, remarkably, comes not from digging but from listening. Scientists use the powerful vibrations from earthquakes, known as seismic waves, as a kind of planetary-scale ultrasound. When an earthquake occurs, it sends shock waves traveling through the entire planet. These waves are our messengers from the deep, carrying clues about the materials they pass through. By tracking where these waves travel and where they are blocked, seismologists can map out the planet's interior. This observation was the first definitive proof that the Earth's outer core must be liquid. Our expedition begins at the very heart of our world, the inner core. This is a place of extremes, a solid sphere composed primarily of a dense iron-nickel alloy. Despite being the hottest part of the planet, temperatures soaring to an estimated 5,200 degrees Celsius, nearly as hot as the surface of the Sun, the pressure here is absolutely immense. The weight of the entire planet above it creates a pressure more than 3.6 million times that of the surface. This staggering pressure forces the iron and nickel atoms into a solid, crystalline structure. Surrounding this solid heart is the outer core, a layer that behaves in a dramatically different way. The outer core is also made of liquid iron and nickel, but because the pressure is slightly less intense here, the atoms are free to move. This layer is a vast, churning ocean of molten metal, about 2,260 kilometers thick. It is the movement within this liquid metal ocean that is responsible for the geomagnetic field. As we ascend from the core, we enter the largest and most massive layer of our planet, the mantle. This colossal layer is approximately 2,900 kilometers thick, making up about 84% of Earth's total volume. It is composed of silicate rocks, which are rich in iron and magnesium. The mantle can be divided into two distinct parts. The lower mantle is solid rock, but under immense heat and pressure, it behaves like a very thick, slow-moving fluid over geological timescales. Above this lies the upper mantle, with its fascinating asthenosphere layer. Finally, we arrive at the surface, our home, the crust. This is the thinnest, lightest, and most varied of all Earth's layers. There are two types of crust. The continental crust forms the land masses we live on, averaging about 30 to 50 kilometers thick and composed of granitic rocks. The oceanic crust lies beneath the oceans, much thinner at 5 to 10 kilometers, made of denser basaltic rock. It is this thin, brittle shell that we experience directly, a fragile skin covering the immense, powerful engine beneath. From the crushing pressure of the solid inner core to the flowing rock of the asthenosphere and the delicate crust we call home, each of Earth's layers tells a part of our planet's epic story.